do you want to look at the data that was measured overnight?
Yeah.
By chance? Okay. So if I go to the experimental data window, I can again highlight it and go say File, Open, and go find it. I can right click. I have the File Open menu right here. Or if it was like recently, like if it was used in the last like 10 or so files, it'll be in the recent list.
Okay.
So we can look down here, and this is probably it right here. So it's a little bit of a shortcut if you want to go find it. If it was not that long ago, I assume it's this guy.
Yep.
Yeah. So here's that data. So that data, again, we let it run overnight. We had the auto retarder on. We did a lot of other stuff. I'm going to clear this off for a second. I haven't tried to fit it yet. I saw it was here this morning. A few things. One is when you've got multiple curves like this, again, you can separate them like this. Sometimes if you double click here, I'll turn off this black default legends. That just puts them all solid colors, so it's easier to distinguish them. Psi delta. Where that gets a little bit goofy is if I double click in this area, I can access here. These are the same menus that are available up here. Just if I double click here versus on the legend, you can automatically get to those sections. Okay. But if you have double axis now, it still gets a little bit like, oh, there's a lot going on. So a lot of times if I have multiple angles, I'm only looking at one at a time. Now it'll fit both psi and delta. If I'm only graphing delta, it's still going to fit psi and delta, or essentially. You can change the fit weighting to do different stuff, but by default, if I'm just because I'm graphing one doesn't mean it's only fitting that. Okay. Now, just FYI. So here, I guess briefly, since we're looking at this, so if we look at psi, again, let's just try to model this real quick. So I'm gonna come over to my model area, and I'm gonna clear this old model out. So I'm gonna say delete model, or right click here, delete model. A couple of reasons I do that is because we had built a structure here. I just want to start fresh. If you had some other advanced settings on, like global fitting, or rename some stuff or whatever, or maybe you had some backside corrections or some non-idealities on, by deleting the model, it kind of restarts it. Now, of course, you could save the model if you liked it. You could save your environment, global save current environment. That saves everything. If you guys have questions with data, I usually ask for the environment so I can see the data plus how you're modeling it. So I see what you see essentially.
Right.
And then I can have a better comment. But here I'm just gonna start fresh. We're gonna delete the model out. Okay. And then we're gonna add. So if you had a model pre-build or environment, we could start from that. We don't have that. So we're just gonna go from scratch. So I'm gonna add a layer. And similarly, if we had added it recently, then it'll be in this list here, or you can go search for it, different areas here, or type it in. So this is on silicon, right? So I'm just going to add SI Jaw 3. That one covers, you can use the standard SI Jaw, that's probably what you used at Missouri. SI Jaw 3, the main thing is that didn't extend as far in the near infrared. So this one was revamped in 2018 or so by Craig. It extends over the full range, and a couple other tweaks, but they're quite minor. So over this range, so you can see now that we did a fine scan, so actually it's probably easier for me to show you. If I say optical constants here, it's going to show me over this what we measured, what they are. But remember when we did that quick measurement, maybe it was this sample yesterday, but we did a relatively short or coarse scan, or maybe it was just the cal wafer.
The cal wafer.
So when I did that, so again, if I want to see the optical constants down here, I can come down here and I can say data, and then current layer optical constants, and then say what do I want to see. Now, if I had multiple layers, do you want to show the substrate or not? Here, I'm going to show the substrate. That's all that's there. Do I want to show just N, or just K, or epsilon 1 or epsilon 2, or both? And then do I want to show epsilon 1, epsilon 2, your dielectric function, or your complex refractive index? Again, it just kind of depends on. These are your settings here, but remember how I said there should have been like 2 bumps when we did that core scan? Well, we did a much finer scan this time, every 5 nanometers instead of every 50. So my silicon optical properties, you can actually see those critical points. Or if I change my wavelength units to EV, photon energy, okay, you can see, sure enough, that absorption, especially if I switch that to dielectric function, you can see, those are energies where your transitions are occurring for that. And then the end's kind of falling in. So out here where you're go transparent or really, really, really absorbing, your index of refraction is high, but it's just got kind of this normal dispersion shape. Okay. Once you have this absorption, the index rolls over. So this is your what we call Kramer's Corona consistency. So one essentially kind of one looks like the derivative of the other. This it's kind of the area under this curve gets integrated. So essentially this can only roll over in n if you have enough absorption, or epsilon 1. So that's again, but it's going to use fixed optical constants for us because the silicon is not. So we're just going to start with that. But if I hit generate and look at say psi or delta, okay, so we can go back here now. I just wanted to show how to change the curves if we want to. You can see here this would be generating for just bare silicon. I mean, what would the bare silicon want? Now your layer on top, it's got a transparent region, right?
Right.
So
it is mostly transparent and around,
maybe
mostly on at least a visible spectrum.
at least above 500, 400 nanometers, it looks like.
Yeah, all the way to 1000.
So if you had optical constants that you're pre-built for this material, you could add them. Here we're just going to use the Cauchy to start with. So that's a nice, easy, transparent model that I can adjust. So rather than assuming fixed optical properties of SiO2 or of aluminum oxide or whatever it is, the Cauchy is an equation that lets me describe, lets me shift that. You know, what lets me change the dispersion. So I'm going to go ahead and go back to my model and say add layer, and either go find it or just type in Cauchy. Here, since I hadn't used it yet, try to type sideways. Here, so again, so you've used this before. Again, you're going to have a thickness. Your A, B, and C are going to give you your dispersion. So again, the manual is really great. It's here. It's long. It'll detail this, but essentially, now I can, rather than assume this curve being fixed, this dispersion curve, I can adjust those Cauchy parameters as an equation to go it. A is essentially where this goes to at infinity, or kind of somewhat your average. If you adjust the A parameter, that just moves your index up and down at all wavelengths equally. You know, it's not wavelength dependent. B and C give it the dispersion. B is over wavelength, and C is over wavelength squared. So you've got so essentially you need to see if you have a wide enough spectral range or a high enough dispersion. But for now, just for fun, we're gonna allow these to fit eventually, at least probably A, B, and C. But I'm gonna say okay. At the moment, since there's zero thickness, I could generate and nothing's different because it's in the model, but it's zero thickness, so it's not being accounted for yet. Right now, the starting optical properties for the Cauchy are somewhat similar to SiO2. Okay, so index around 1.5, 1.45-ish. So we can start with that. I need some thickness here, so I'm just going to go ahead and mouse roll this. So I'm going to hold down the Shift key. Click on it, so it's ready to roll, and then hold down the Shift. That's 1 nanometer at a time. If I hold down Shift Control, it does 10 nanometers at a time. So you can see if this was say something close to SiO2 on silicon, it gets thicker. Those interference oscillations are going to redshift. Basically, that interference pattern is going to redshift, and you're going to develop more of them. Now, if this was really, really thick, we'd have this. So I can now the index might not be perfect, but I can get a rough idea what the thickness is with the assumption it's something like SiO2. Okay, and this also assumes that we are transparent, i.e., K is equal to 0 right now. Currently the Cauchy is, you could add stuff to make some absorption in there, but that's essentially what we have. So the thickness with that assumption is around maybe 180. Now if we look at delta real quick, just a couple side notes, that also came along for the right, that phase term. Now sometimes it gets brought up, why is delta changing so much right here? Okay, remember I said delta is a phase. So right now, since we use the auto retarder, since it sits for long enough, it'll close the slits. So since we use the auto retarder, delta, I was able to measure a full 360 degree range. So it's like a circle. Every 360 degrees it repeats. You have the wave delay. You got one wave path. So essentially, twofold. If you use the auto retarder, you can graph it over a 360 degree range. If you don't, you're going to see this over a 180 degree range. It's going to keep wrapping around. Okay. So what happens is we graph by default that delta range from -90 to +270, because things like glass, you have an oscillation around 0. So otherwise, you have these steps always at 0. So these, where it looks like sharp features, are just simply wraparounds of the graph. So delta is trying to go above 270. We said no. 270 is equal to -90. Start it so we can. Otherwise, delta would just keep going off the graph.
Okay.
So because delta is really, if it was an absolute, so it's every 360. So this is really a wrap. So you can change that. I'm not going to do it now, but if I go down, to my model and say model options, or if you just left click right below the model, that's a shortcut to model options. Here, where is it at anymore? I don't usually change it. There's a minimum delta. Here it is. So your minimum delta by default is minus 90. You could change it to 0, then it would put your range from 0 to 360 or whatever you want. But again, so it's not an artifact in the data when it does this. It's just trying to grab delta. It's trying to wrap delta in a graph. That's really what it's doing. If we briefly look back at psi, so now it's like, well, again, especially out here, we'll adjust that in a little bit. I'm just gonna, I know it's probably more transparent in this range. We'll expand it later. So I'm just gonna go to my range, my data section, say range select. I'm gonna look, let's look at above 500 nanometer for now. So let's try to fit this data first. And so you can see, this is the assumption of it being something near SiO2. Now I can fit from now, I could allow it to try to adjust the A and B term if I want, but I can also mouse roll those. It's just a little bit more of it's an extra step to get to that location, so I'm going to show you where that is. You need to have it on as an active fit parameter, like I do. And once it's an active fit parameter, you can come down to your fit section here, and you can say basically edit params. Okay? So if you get in the edit params window, now I've got my active fit parameters here. You can set up things like global fitting. That's going to do some searching for parameters, a wide range search, stuff like that. Or the main trick here is I can basically come in here and go to say the A parameter, and now I can adjust it here. So if I mouse roll it here, that adjusts the A. So you can see essentially when you have a transparent film on say silicon and it's thick enough to develop interference oscillations, psi is nice to look at because now that I have this interference oscillation, essentially the peak to peak height in psi is really hyper dependent on the index contrast between the film and the substrate. So if my silicon I showed had a refractive index around 3.5 to 4. The film currently has a refractive index around like 1.5, 1.45, 1.5. So very, very different refractive index. So that would be a big peaks in psi. Now the similar the film is to the substrate. So if this same film were on glass, your psi peaks would be very small because you're very small optical contrast. The index is about the same. But if this film gets close to the silicon, that's going to also bring these peaks down. So the silicon, so essentially one of these sides is kind of the silicon side. So if I were to set my film thickness back to 0 for a second and just generate, let's just do that so it kind of stays there. If I just generate now, if we had a lot of interference oscillations, you can kind of see this envelopes here. So it depends on if you're above or below Brewster angle and if your film's higher or lower index. But in general, one of these envelopes kind of sets the refractive index of the substrate if you just have a single layer transparent film on it. The other one is your optical contrast. If this is a very, very large index difference, the more index contrast you have, the bigger these peaks are going to be. The smaller, if it's transparent, the smaller they are, the closer the index. So we'll go back. So I just kind of want to show how you can mouse roll that too. So we'll go back. So again, we could just tell this to fit and see where it wants to go. It's kind of demonstrating that a little bit. So let's get back to about the thickness. But you also notice as I change my index, edit params, and I change that A parameter, I can also change the thickness here now. Again, as I get closer to the index of silicon, notice how those dampen. Okay. If I get closer, away further that, they go actually up. Now if I keep going down, they came down in for a second. You can see there's a little bit of a range here where actually they went down and then back up. That's because you do have another interface here. That's air. So you have air, then the top of then the film, and then so you have an interface of the air versus the film and the film versus the silicon. So you have that also comes into play a little bit. But you can see that we're kind of in the ballpark here as this changes. The other thing to note is remember when I changed thickness only, it just did a lateral shift. The peaks stay the same. When you change the index, it changes the peak to peak height, but notice it's also doing a lateral shift. That's because you're changing the optical thickness. It's because your index is changing. Well, that's also going to affect this left-right. So at the end of the day, usually if you're just fitting a Cauchy, if we can assume it's transparent, we can say, I'm close enough now, let the software fit this. So Control F or right-click normal fit, or highlight here and come up to normal fits and say normal fit. So different ways to get to there. So we can say, hey, let the software adjust those parameters to get the best match. The thing is, I need to be somewhat in the ballpark. If my peak was way over here and I said fit, it's too far away from the right solution to figure it out. So that looks, so currently it looks like this wants to be, at least for the measurement we did, close to 200 nanometers, a relatively low index. Is this the porous one?
Yeah. Okay.
And it's assuming it's transparent still. Delta, and let's look at the dipole real quick. We do have some depolarization since we measured it.
Mm-hmm.
Okay, so that could be twofold. That could be, again, we did use the collimated beam here.
Right.
So that was a much, you saw my business card earlier, that's a pretty large area at 70
Mhm.
degrees we measured. So that could be some non-uniformity.
Mhm.
Especially since you're thicker, you might be sensitive to it. So I can try stuff like that now that it's easier to see it with the dipole. So that's going to dampen these peaks is what's going to happen. So if I want to account for that in this
Mhm.
case, I can come here to my model options. So I left click under here or go to your model window and say options. I mean, that's the same window.
Mhm.
And we can test for some non-idealities. So I can either just do thickness non-uniformity or I can do multiple. Now you don't have to worry about angular spread because you don't have any focusing right now.
Mhm.
You'll always have some bandwidth. That means like I see plus or minus light. Here, if you have thickness non-uniformity, the beam is seeing multiple thicknesses. So I'm at the moment I'm going to turn them both on just to kind of show the difference. I don't know if I'll fit them both or not, but I'll just explain it real briefly. So let's look at one angle here just to start with, just so it's not so many curves. Here, okay. So it's like a 70 degrees to start. So you can imagine this was the kind of the fit or the assumption that everything under the beam was uniform. It only has one thickness and one set of optical properties underneath the probed area. We measured a certain area. Everything is perfect. That's what it's predicting right now. But you can imagine, again, as I mouse roll this, let's say some of the beam was the average, but some of the beam saw something this thick, and some of it saw something 10 nanometers less. So if under the beam you average that plus that plus that, essentially what happens is anywhere you have a peak in the data, your actual measurement is going to be suppressed. Because if I average this curve plus, so if you're on a slope, they actually on the slope here, they actually average back to, so if I that plus that plus that, it actually averages back. So that's why we're seeing depolarization at the peaks, because you could have a non-uniform film and you'd still get the same psi measurement here, because those all get the same back if you have an average. Here you don't get the same psi measurement because you have mixed polarization states. So what that really means is, essentially part of the sample, most of the sample was elliptical, like this state, at that wavelength, wherever we're at. Well, but where it was thicker, it was a little bit shifted ellipse and a little bit shifted ellipse. So you're measuring the depolarization is essentially a mixture of polarization states. So it's not just it's not just all this one state. It's this plus or minus a little bit of a smearing or a spread. So it's a little bit fuzzy because it's averaging those together. So that can either be due to, in this case, thickness non-uniformity, or it can be due to bandwidth. So we ended up, now there's not a lot of bandwidth here. If I go to the file info, so file information, so I can see what our slit was set to 1,000. So that's essentially a 1 millimeter slit, 1,000 microns. On the main, that's probably a little bit more here because we measured out a little bit these longer wavelengths, but the primary grading, it's 2.3, 2.4 nanometer bandwidth per 1 millimeter slit. So if I wanted to simulate that just for fun, if I came in here and I said, well, let's just say we had 2.3-ish, 2.4, okay, bandwidth, and I just generate that. Okay, it didn't really influence that too much. And how much dipole did it predict? Almost none. So I would have, even if out here it's probably on the next grading, so it actually might be double that. But let's say we did have 4.6. I'm just kind of simulating. Eventually, there's a little bit of a bump here. So now farther in the UV, that would become more important. But you can see that you need a heck of a lot of bandwidth to describe that. Edit. So you could always fix it kind of at a nominal bandwidth, but sometimes it just depends what's the dominant effect. I can guarantee that I can't go past 30. We don't have 50 nanometers of bandwidth, okay? Yeah. So either I say, well, the dominant effect here is the thickness probably, or they don't just add up together, but sometimes I just say, oh, I know what my bandwidth is, I'll fix it here, I'll add the rest into the thickness beyond uniformity. Both could be similar. So if I change that, change value, oops, I want to go 0, sorry about that, 0, change value. So if I instead add some thickness non-uniformity for fun, you can see it doesn't take too much, but sure enough, 8%'s, that's a pretty large area. I don't know if that's fully correct, but you see it accounts for that. Okay. But what it really might be is I really might have, say, let's say 3 nanometers of bandwidth or something. But that does, and maybe 7% non-uniformity or something. So there might be a little bit of a mixture, but they do a very, very similar effect. So just kind of keep that in mind. So you're going to get a similar thickness result, but for example, if I fit this now with just fitting, let's assume 0 bandwidth for now, just to show one at a time. If I look at all angles, so we'll say, let's basically say the full range, 0 to 90. So I've got all angles now, and I generate. Now it looks like there might be a little bit of difference per angle, and that makes sense because remember my beam is spreading more versus angle. Right. So if we were at the center of the same average, great. But if your beam spreads and it's more non-uniform over here versus over here, you might have a difference there. So these are a little bit minor at the moment, but that's part of the misfit here. Is probably so if I had changed some stuff here, but my thickness was right at 200 or so before. So if I add that, I probably have a little bit better MSE by adding some thickness to uniformity. We're not perfect, but we're closer. So regardless, it's around 200 nanometers, and your index wants to be in this spectral range around 1.4. Okay, because you said this was porous, right? So you could.
I think it looks like it's completely collapsed.
Because what were you normally getting for an index?
For a porous film, we can go down to 1.19 to 1.2.
Oh, that's really porous then, yeah.
Yeah. But it looks like this is. We were having some problems with the films lately.
Okay.
So I'm not surprised.
So this has a higher index. Yeah. I mean, if this were a lower index, you could see that directly. So again, just from a standpoint of looking at side, right? So again, if this is currently at 1.38, but if this was really around closer to 1.2, that'd really be suppressed.
Yeah.
So it is. Especially out here where it's mostly transparent, or basically it's transparent, I think we're good to go. And so if I want to test something else, we can either expand the range or do some other testing here. But again, when I'm at especially if I'm going to just try some stuff, and I'm like, oh, I like where I'm at now. If I goof it up, I don't really want to start all the way from scratch. I want to save this model. So this is where I would normally save myself. I save environments. So if I go to this global menu, I can say save current environment. And then now it's where do we want to save it? Probably VASE folders. I'm just gonna put it back in my Greg install. This was, what was this again? NPO.
NPO, yeah.
NPO. We'll just call that Koshi or something. All right. So, whoops. No, good enough. I actually hit caps lock, but good enough. So that way, if I goof something up, I can just load that environment and it's like a save point. Okay. Or that, that's what you could send to me. Now you could do, it really depends on what you want to test here. If you want to try to fit the full range, so I can range select all. If I just hit generate now, it's going to extrapolate the Koshi optical properties down there and just say how does it match. And actually that looks still pretty good. Yeah. So that means, to me, that means that the assumption that the film is transparent is still happening down here, which is nice. Yeah. If this was way off, let's say that the prediction was here, but this kind of dampened off, that means your film became absorbing, so it dampened the oscillation. Right. So I will likely get a similar thickness. My MSE is, so if I say fit, so my MSE went from like a 20 to a 22, but I get the same thickness, I get the same Koshi results because it was already predicting it well. If it didn't, and you wanted to fit that range, we'd have to add some absorption. So there might be a little bit of something there, but for the most part, that looks pretty good. Again, you're gonna get more dipole because those are sharper down there, but it's still predicting it. This one that's probably misfitting, my guess is, just for fun, sure enough, this one that's got the higher dipole that wasn't fitting is a 75 degree. So in that one case, the beam was 4 times the width. So the beam was really big. Yeah. So that makes sense. You could fit angle dependent dipole, but that's nitty gritty stuff. So that gives a similar result. Since it's that wide of a range, we might try the C parameter to see if that cleans it up a little bit, but it really didn't help. So same MSE almost. C is so small. Yeah. It's essentially the same model both. I mean, C is almost so small, but at least the error bar here is less than the value, but it's maybe like 20% of the value. So you could have with or without C in this case, it doesn't matter. The very last thing I would try for fun, which I don't think is going to happen here, but we'll just try it to see if it changes anything. I'm going to try to add uniaxial anisotropy, because I mentioned sometimes you have these porous materials. Depends on how it stacks. Sometimes it's not uncommon for these to exhibit some type of uniaxial anisotropy. So I'm just going to check real quick if it does. if it wants it, and if it does, I'll show you what I'm doing. So the main thing is, so I try to add it. So what I did was I converted this to a uniaxial model, took those Cauchy baseline output constants, and it's going to start with those, but it's going to say, hey, I'm going to use that same Cauchy value for the n and z, or I'm sorry, n or x and y, and the n plane index, n, x, and y, but I'm going to allow it to be different from the n, the index of the z direction, your out of plane. That's the uniaxial, just assume normal. So x equals y does not equal z. Okay. So the way WVASE does it, it builds up dummy layers. So it starts with, so when I right clicked on the Cauchy and I added uniaxial, it built the structure for me. So it started with my baseline end plane properties like we already had, and instead of fitting independent Cauchys for the z, you can do that too. It just said, well, I'm most sensitive to the difference. So it just said, start with these, and to calculate z, use a difference function. And so this difference function, you could have it be wavelength dependent and stuff. By default, the equation here, if I only fit a, it's a times 1. So it's just an offset. So it's just fitting an offset to calculate it. So here it didn't improve the MSE. And if that MSE dropped from a 20 to a 10, I'd be like, hey, this might be showing uniaxial anisotropy. But that's the other thing I would kind of check on the sample. So the index
grading of the optical constant,
or a gradient, exactly, yes. If we went back to the here, yes, you could always try to add like some simple grading just to see if it wants it. So usually I bump how many steps it has, turn off symmetric, and just do a quick variation. Same comment. It took those Cauchy values and it's allowing them to vary. By default, there's no grading, but if I allow some, same comment. You're testing to say, hey, this was already a good fit. If this fit was poor, then I'd be trying these things, and one of those might be Y. So so in general, I think so it might be a little bit higher index, but like you said, that might be because it's just not. Hey, how are you doing? That makes sense. I mean, similar. I mean, you've done that. That's what you do. This is the same stuff you've done before. So, but we didn't need that higher resolution last night, but I didn't know. So we did a really long measurement, but that's essentially what.
But we need to have a lot of polarization, right?
Again, especially at the low wavelengths, but it's going to be easier to. It doesn't take a lot of non-uniformity to have that. So that's it's 5% That biggest angle had some because I think it was just sampling a wider area and probably seeing more non.
So an auto retarder was not really necessary for this.
Well, so I guess that's a great question. So twofold. If you didn't, I can't simulate necessarily without the auto retarder what delta would look like, but if you didn't use the auto retarder, and we didn't need 4 angles either, we just let it run overnight. But we had like 2,000 measurements or something. It was a lot. If you didn't use the auto retarder, again, this wouldn't go over the full range, but you would likely have gotten the same solution regardless. What I will say is that if you have depolarization present, you saw how that influenced. So again, as I influence this, so I guess we could look at this graph here. But as I, for example, gave it more or less thickness non-uniformity, you see how that's going to affect those peak-to-peak heights. That's going to dampen those. So the influence of actual non-uniformity is going to show up here. It's just whether whether it's dampening because it was non-uniform or if it's dampening because your index was different. It's a little bit harder to know if you don't have the depolarization. The depolarization gives you the if I needed to dampen that and had no depolarization, then that would give me more justification. Hey, it's not thickness non-uniformity, but the fact that there's some depol there gives me justification to add the non-ideality. Does that make sense? So you could account for it without the depol. You would just be more of a you'd have less confidence that that's the reason why.
Okay.
Very cool.